Welcome to Late Times in the School and Chaos. Okay, so today we'll talk about what happens in chaotic systems, quantum chaotic systems at late time, and how to diagnose that, and also what has happened in the experimental literature and what may be coming down the road in the future. So I'll start on the board as before and sort of sketch out some ideas. First about late time dynamics, and then a little bit about the experiments. And then we'll go again to the slides and see some figures, and then talk about some of the experimental aspects. Okay, so recall last time we saw that there were various notions of decay and scrambling and chaos that we could define at short times in a many-body system. And we could associate different notions of chaos with decay of one-point functions or two-point functions or four-point functions of various types. But even in a local system, all of these things would decay on a time scale which was controlled by the total number of spins, by the entropy, perhaps to some power, but still a relatively short time. Okay. Nevertheless, in the first lecture, I showed you that the thermalization will persist for a very long time, and the recurrence time may be even longer still. So you can ask what's sort of going on in that very long time after the initial onset of scrambling, the initial onset of the sort of totally delocalized information. And one point of view, from information theoretic point of view, is somehow the state is becoming more scrambled in the sense that it will be harder and harder and harder to recover the initial information as a function of time, meaning that sort of the size of the operation you would need to do, the number of gates you would need to apply to retrieve the information you put in is growing with time. And from the point of view of chaos as sort of being about effective randomness, one of the key ideas going back to the 70s is and building on going back to the 70s, it is the idea that the spectrum of a chaotic system, the energy level spectrum, should be like that of a random matrix. So that's a sort of strong sense in which a quantum chaotic system is sort of effectively random. If you look at very late times, you look at this spacings of different eigenlevels, you find that it's essentially distributed like the spacings of a random matrix. And random matrix theory has a long history in physics, going back at least to Wigner, who said, let's think about nuclei. They're very complicated. They interact in a difficult to understand way. So maybe it's sort of generic, and the spectrum is sort of like random matrix spectrum. So then in the 70s, it was sort of understood in the sort of old quantum chaos literature that this random matrix spectrum would also be expected for a quantum chaotic system. So that's what we'll mostly talk about today. So late times, we have, again, a Hamiltonian. I won't write it again, but the basic thing now is to consider the energy levels, the microscopic energy levels, the energy eigenstates and energies for the whole many-body system. And recall that for n qubits, the dimension of the Hilbert space is 2 to the n. Since this is a Hermitian operator, its basis must span the Hilbert space. So here I runs from 1 up to 2 to the n. However, the largest and smallest eigenvalue of h is of order plus or minus n, because there are only order n terms in the Hamiltonian. So even if all the terms sort of lined up one way or the other way, you could never produce an energy larger than n. So the EI are going to live in something which is roughly minus a constant times n to a constant times n, like that. But I need to squeeze exponentially many eigenvalues in there. And so just by counting, you see that unless there is huge degeneracy, it has to be the case that the splitting between some of the eigenvalues is very small, of order e to the minus n. So unless degeneracy, and let me define, so I'm going to always take the EI to be ordered, meaning EI plus 1 bigger than or equal to EI. And then we can define a splitting, delta I, which is just the difference of the EIs. Then unless there's degeneracy, very large degeneracy, the minimum over delta I must be of order 2 to the minus n. Now, okay, there's a factor of n here, so that can make it a little bit bigger, but this exponential suppression is the dominant effect, and so you would sort of generically expect splittings at least this small and maybe smaller in some cases. Just because you have to fit so many levels into this non-exponentially sized window. Okay, and so the claim 1, and this is a very traditional definition of quantum chaos, is that if I take the delta I and I normalize with respect to some kind of average level spacing, that these numbers, if I plot them in a histogram, say, will obey the distribution, the same distribution as you would get from the level spacings of a random matrix. Right, so these things are distributed according to the splittings, the normalized splittings of some Gaussian random matrix. So what this means is I have here the Hamiltonian was, as we discussed extensively before, it was sum of local terms, or maybe non-local terms, but it's still few body. But here, this random matrix would actually be an exponentially large 2 to the n by 2 to the n random matrix in which every element is non-zero. So it's just, you can think of this thing as I have a probability for some matrix M, which goes like e to the minus some constant times trace m squared. So if you write out that trace, it's like every component of the matrix is just a Gaussian random variable.
So is the splitting of the statistics also?
Well, so yeah, so sorry. The simplest thing is just like a histogram, like the density of splittings. But then, of course, you also want to look at the correlations of the levels and things like that. Is that what you're asking?
Yeah. And
Sorry. Yeah. So, yeah, we'll see that. Okay. And claim 2. So this is a common definition of quantum chaos. It may still be, it may be the right definition of quantum chaos. This is certainly a good definition. But from the point of view of this definition, one thing you should ask is whether you necessarily recover all of the physics we saw at early time. If you want that early time physics to be a part of what you mean by quantum chaos, then you need to prove a theorem which says that if you have such a statement plus locality, then you get all that early time physics back. And that may be true, but as far as I know, that theorem does not exist in any great generality for a quantum many-body system. For systems that have a classical limit which is chaotic, we have some evidence and some results that establish a statement like that. But in general, as far as I know, I think it's sort of an open question. The claim 2 is that the energy eigenvectors, quote unquote, look thermal. And this is called the eigenstate thermalization hypothesis. So it's sort of a state-based version which you might associate with chaos. And these are sort of both very long time phenomena precisely because the level spacing is so small to really isolate a single energy eigenstate should think of that as corresponding to some exponentially long process in time. And what look thermal means is that the trace over some region A the complement of some region A in some energy eigenstate, EI, is approximately the same in some sense as the trace over the same thing in the thermal state. Like this. And so here the temperature is determined by the energy of this state. You find the temperature such that the average energy of this thermal state has the same energy as this state. That defines the temperature. And then you're supposed to look at, say, subregions and compare the density matrices. And so to make this more precise, you would need to specify for what regions A and A bar you're allowed to do this and how precisely equal they should be and for what observables. Okay. So those are two things that you can diagnose. And the final thing that I'll show you, which gets at this question of the level spacing statistics, the correlations between different levels. So I think these are sort of the two main claims, but there's another useful diagnostic. Which I'll show you for claim one. I'm going to focus on, I'll show you a little bit of data for eigenstates, but I'm going to focus on this because it fits more into our sort of thinking about timescales point of view. And in fact, as far as I know, this is not obviously related to this. I mean, you think they come together, but again, I don't think there's any general proof that this is the case, although I'm happy to be corrected. But a useful diagnostic for claim one, for looking a little deeper, is to look at what's called the spectral form factor. So this is defined as follows. You take essentially the expectation value of the time evolution operator in some, say, thermal state, which is defined like this. So this is just the expectation value of time evolution operator. That's this e to the IH in the thermal state. And you sort of look at the 2-point function of this thing. So you can take U dagger, and you can perform some kind of average. Now, what this average can be depends on what you want to look at. In the cases I'll show you, what we'll do is we'll add a little bit of disorder. So a little bit of a randomness to the Hamiltonian, so like a small random component, which is fixed in time. And we'll vary this small random component from system to system. And we'll multiply these two. We'll calculate this for each realization of the disorder. And we'll multiply them together, and we'll perform the average over different disorder realizations. And that quantity will define this 2-point function, essentially, the level spacings. Okay. And then we can also define a connected part of it, which is also interesting to study. In which we average and then take away the 1-point function like that. And if you don't want to introduce disorder, you could also try to average over time, like to sort of smear this in time in some way. That would be one possible way of defining this quantity without disorder averaging, without changing the Hamiltonian a little bit. But here I'll focus on the disorder averaging case. Okay. And using the code I provide, you can also check what happens if you don't disorder average and formulate some hypothesis about how these things are related to each other. And this quantity in particular, you've heard a lot about chaos and black holes, which, as I said at the beginning, is one of the motivations for the revival of interest in this subject. We haven't really heard anything about this late-time physics of chaos yet. So I should mention that this quantity, the spectral form factor, in the context of the SYK model and also in the context of conjectures about quantum gravity, recently appeared in a very nice work, including, let's see, Jordan is here somewhere. There's Jordan, Masanori, and various other people. There's an enormous, it's like an experimental paper from CERN, but for random matrix theory of black holes. So I encourage you to go talk to them if you want to know more about what's going on there. As always, I'll show you the values, the way this looks in this parallel quantumizing model, and you'll see the similarities and differences. The other thing I'll say before moving on is that here I didn't make any statement about whether the Hamiltonian was local or non-local geometrically. And you might naively think that at such late times it doesn't matter whether it's local or non-local because particles have had enough time to move all around the system many, many, many times. And so it shouldn't matter too much whether the interactions were originally nearest neighbor or whether everyone could talk to everyone, because the time it takes for these kind of phenomena to manifest is so much longer than the time it takes for a particle to move across the system that it may as well be non-local. So you might have a hypothesis that local and non-local, but still few body Hamiltonians behave in the same way as far as these measures are concerned. And that's a hypothesis that one can try to check, at least at late time. Okay? Any questions about this stuff? Anything? Yeah.
So you're using the spectral form factor simply because it's easier to refine than actual correlators?
Yeah, so you can certainly look at actual correlation functions. I wouldn't say it's easier to define. I would say it's sort of a more invariant notion. I'm sort of taking out all the information about matrix elements. So it's just focusing on the spectrum and not any peculiarity of the particular operator. But you can certainly look at single operators.
Do you expect to be able to get the Atómico exponents out of those? Or?
No, not necessarily. Yeah, this is some very late time thing, long after anything associated with the Lyapunov exponent is done happening. So it's not clear to me that there should be any signal of Lyapunov exponent here. For example, you might hope that something like the following is true, that if there's a Lyapunov exponent, then you get this behavior at late time. But it doesn't necessarily imply that the Lyapunov, the detailed value of it, should have any impact. Indeed, the hypothesis here, which is that it's just determined by a random matrix, that doesn't know anything about the Lyapunov exponent, because it's a totally non-local Hamiltonian. So sort of the hypothesis is actually that at late times, all that details about local, non-local is just gone, and you just have random matrix theory. So perhaps the crossover from the sort of local physics to random matrix physics, you could observe some signature of the Lyapunov exponent, perhaps. But I don't know. I think this is an open question. Okay, so I won't keep you in suspense. You know, these things will work approximately for the PQIM model, also for this random spin model I showed you. But I'm going to defer the data just a little bit because I want to talk a little bit more on the board about experiments before we go on. But so here, this is sort of the end of the discussion of chaos in this model. And so I'll just pause here and see if there are any additional questions. Yeah.
So in this ETH thing,
Yeah.
I just took any state and I traced out some subregion. In the remaining subregion, I guess we know it would look sort of thermal with respect to the modular Hamiltonian. Is there any relationship between that fact and this?
I'm trying to understand in what sense that's not just a definition of the modular Hamiltonian.
It is.
Okay. Yeah, so then I guess in that language, I would say the statement is that the modular Hamiltonian for energy eigenstates is approximately the thermal Hamiltonian, just the ordinary Hamiltonian. Like in other words, if this is literally true, so it's not exactly the Hamiltonian because this Hamiltonian cuts across A and A bars, so when you do the trace, you're going to get some boundary effect. But I'd say up to sort of boundary terms localized on the entanglement cut, the entanglement Hamiltonian of an energy eigenstate, the modular Hamiltonian, is just the physical Hamiltonian. That's one of the statements of eigenstate thermalization. Other questions? Okay. So now let's talk about experiments. Okay. So we're going to rewind time all the way back to the start and ask, go back to early times, because as we'll see, experiments have no hope at the present of probing this kind of physics for even 100 spins, because it's just too distant into the future. So we're going to go back and ask now about, what experiments can do and what they might be able to do soon. And it sort of mostly involves early time physics. Okay. And so I'm going to introduce things sort of historically and talk about NMR systems. It stands for Nuclear Magnetic Resonance System. And I'm actually going to introduce the idea of the Hahn echo, which is probably the first experimental realization of some kind of time reversal procedure in a mini-body system. And then from that, we'll sort of build out and understand some more modern experiments and what they're capable of. So I'll tell you about the Hahn echo, which comes from a paper in 1950 by Hahn, for which he won the Nobel Prize. The idea is the following. So suppose you have a collection of spin-a-half moments in some material. And let's say, for simplicity, I have a magnetic field which is coming out of the board and which is strong. So I have lots of spins, lots of sites in various places in my material. They may be arranged regularly, maybe disorderly. It doesn't, for the purpose of the discussion, doesn't matter too much. And let's imagine that there's a strong field, magnetic field in the z direction coming out of the board. And let's imagine that I've initialized all my spins in, say, the plus x direction, just for purposes of thought experiment. Well, then the Hamiltonian of this system is simply the sum of over all of the spins this is the simplest possible Hamiltonian you could think of for this kind of thing, right? Where there's a uniform field and all the spins experience the same field and they just have Zeeman interaction. Right? And now what will happen as a function of time is that because these spins are in the xy plane, they'll just rotate uniformly. That's what spins do. They process around the field direction. And so if you look at the magnetization, say, in the x direction as a function of time, it'll be something like the number of spins n times cosine bzt. It'll just oscillate. Right? It starts out at 1 and it recesses, but all the spins have the same frequency, so they just rotate as one giant spin. However, this is not really a physically realistic setup because typically the spins will each have their own local environment. They'll have some differences in how they experience this field. And so a better model might be that, sorry, this should be R. There's some local effective variance, say, in the magnetic field. And now what would you expect to happen? Well, now the magnetization as a function of time will be the sum from r equals 1 to n of cosine bz plus delta br of t, like that. And if this delta B is some kind of uncorrelated fluctuation from spin to spin, then what you're going to have is a sum of lots of terms from between -1 and 1, but they're all kind of rotating out of phase, right? So some of them are pointing in this direction, some in this direction, some here, some there, some in their intermediate value, and it kind of varies from place to place. So the simplest model for that would be a random walk, in which case you expect the value of this magnetization to be like square root of the number of terms, so that's like square root of n. And if n is a large number, then this would be a very substantial reduction in the magnetization that you would measure experimentally. It would go from n to square root of n. And that's just caused by this kind of essentially dephasing dynamics due to the fact that you don't know exactly how each one is rotating, and you're trying to make this microscopic measurement. Okay, so the signal would decay very rapidly. However, you could fix this problem with a simple trick. So this is sort of what the signal might look like as a function of time. It starts out, magnetization over n starts out at 1, say, and this is the ideal curve would have some big oscillations. The truth thing that happens, you have oscillation, and then there's some kind of decay, like that. Let me draw it a little bit better. I don't want to say too much about exactly what this decay should look like. I don't want to get into the details here. But there'll be some kind of decay, which comes because these things are all oscillating out of phase. However, suppose at some time t star, we apply a pulse which talks to all the spins uniformly. We just apply this thing, right? Let's call this operator Q. So now what happens to the Hamiltonian if I conjugate by this operator Q? Well, it's a sum of z terms. Every z anticommutes with x. So I simply get minus the Hamiltonian. Like that. Right, for each term here, just look at one z, I have sigma x, sigma z, sigma x, which is minus sigma z. So by doing something uniform to all the spins, without any knowledge of what the individual fields are, I nevertheless effectively change the sign of the Hamiltonian from plus to minus. So now if I evolve again for another time t star, what will happen? This decay will just disappear, and I'll immediately revive the entire spin, like magic. Okay, so evolve for t star, apply q, evolve for t star again, and you get a revival or an echo. Okay, and Hahn, I think, recognized very early that this was really about reversing time, essentially, in this very simple system. Okay, and I won't go into it, but this is now a very useful tool, and it's sort of a basic part of the experimentalist toolkit for dealing with NMR system. Precisely because you always have this kind of uncertainty, but you can use this echo procedure to sort of mod out its effects. However, of course, this is still an idealization because the Hamiltonian is never going to be this simple sum of non-interacting pieces. There will always be some residual interaction. And so in reality, in a sort of real experimental system, unless you've taken great care to isolate things or to make the Hamiltonian that Hamiltonian, the Hamiltonian will be, let's call it H prime, will be H plus some, say, perturbation V. And V may be a perturbation that couples different spins. It may have some structure. And so this is the sum from r equals 1 to n of sigma rz and this perhaps is some interaction or some other term that you don't control. And so now what will happen is if you perform this echo procedure, you'll see that as you make T star longer and longer and longer, even the echo will eventually decay, precisely because you're not reversing in time this other term. The spin echo only reverses this. So let's suppose this is the dominant interaction, but nevertheless there's something else here. Then the echo will be imperfect, you'll eventually lose coherence, and that's associated with a time that's called the T2 time in NMR. Okay, so the decay of this Hahn echo. And this T2 time, and maybe the sort of one simple manifestation of the scrambling or chaos that happens in this more complicated interacting system. Okay, now then, let's sort of go forward in time. As a function of time, experimentalists were very clever, and they come up with better and better ways of reversing interesting Hamiltonians. So even if the Hamiltonian had some interaction, say dipolar spin interaction, they could, via various tricks, partially reverse that Hamiltonian. So more modern experiments maybe this is some kind of interacting spin model. And then via some procedure, you can reverse to another Hamiltonian which you might call H plus V, say minus H minus V, but plus V prime. So this sign is crucial. So in other words, I'm saying you get better tools, better control of your system. You can reverse and control more of the Hamiltonian, but there's always some perturbation that you don't control. And then what you can observe is that even though this perturbation can be made quite small, the echo still decays on a relatively rapid time scale. And this really can be interpreted, going back to work of Horacio and his collaborators, that the decay of this thing, even for very small perturbation, can be a measure of chaos in this system. So this is really what I told you yesterday about the Low-Schmidt echo, where I have a many-body interacting Hamiltonian. I have a small perturbation. Even when that perturbation is very small, the echo will decay rapidly precisely because this system is already chaotic. And so even though I'm making just a small perturbation to it, I've worked very hard to isolate and control the system very well. This small perturbation, it does eventually have a large effect. So there are many experiments here. I'll list a lot of them in the lecture notes, so I won't go through the details here. But this is the basic, I think of, the 5-minute picture of NMR and echoes here. So what I want to do now is go to the slides, show you first the late time physics, and then also show you the current experimental situation in the quantum optics community, which means things like cold atomic gases, trapped ions, and others, where we can try to construct and isolate very complex many-body systems of a larger size than were possible before, and for longer times to probe this physics in increasingly complex situations. And then at the very end, I'll end with a sort of pictorial discussion of the future. Let's see if this works. Okay, great. So, late times. We're jumping forward in time again. That's the theme of this, this lecture course. You can go forward and backwards and learn something interesting. So, yeah, So here again is thermalization. You see this early time decay, it decays, and the decay lasts a really long time, that's what we said. So what's going on in this region in here? Well, here's what I told you. I have some spectrum and some energy eigenstates, and that these delta i's, these splittings, are like the splittings of a random Gaussian matrix, and that the energy eigenstate should look thermal in some sense. So here, let me show you now an example of this for the model we've been studying. And I'm just going to, for convenience, add a small random field. So this random field, which varies from site to site, but it's time independent, just makes this level spacing a little bit nicer. You have the code, so you can check what happens if you don't have this. And I'll show you now a histogram of the level spacings, these delta i's, but normalized by the mean spacing. So I average the level spacings. That gives me some overall unit of energy. I divide everything by that, and I'm going to plot that in the histogram form. So here's the result of that for n equals 12 sites with small random fields. I had 25 bins here. This is the normalized level spacing on the x-axis, and the probability that you have a certain number, that you're in a certain bin on the y-axis. And the data from the model are these blue bars. And then I've shown you overlaying that two curves. One is for a so-called Gaussian orthogonal random matrix ensemble, and the other is for a Poisson distribution. So what do these two things mean? Poisson is what you would expect if all level spacings are kind of independent of each other, if there's no level repulsion. You see there's a high weight to have small level spacing. That is, the levels can be quite close. But what you observe in this data is that actually the physical model has a very low probability of having energy levels that are very near each other. And actually the distribution of levels follows relatively closely the distribution of levels you would have in the Gaussian orthogonal ensemble. And why is it orthogonal and not something else? It's because this model has a time reversal symmetry. It's not the time reversal symmetry that you're familiar with from spins, where all the spins go to minus themselves. I've added an extra unitary operator to that, a kind of charge conjugation. But nevertheless, it is an anti-unitary time reversal symmetry, and so that's why you get this Gaussian orthogonal ensemble. At a more elementary level, it's just all the matrix elements are real numbers of the Hamiltonian. Okay? Now, what happens? Oh, yeah, so here is now the second claim, the entropy, the eigenstate thermalization. Here I plot as a function of the energy of the eigenstate, the entropy of site 1. This was our sort of simple diagnostic we saw in time evolution. At late times, the entropy of site 1 approached 1 bit. That was corresponding to the maximally mixed state when I started my system in this plus all y state. And remember, the average energy of that plus y state was 0. So it sits right here. And now if you look on this curve, this is the data entropy of site 1 for every single energy eigenstate. There's a lot of them. They cluster up here because that's where the density of states is the highest. And you see up there where the average energy is close to 0, which is what you have found that you'd have for this state, the entropy is very close to 1. Okay, for lots and lots and lots of states. So for a very large part of the spectrum, which have average energy close to the value here, you see that the entropy of the first site in the eigenstate is roughly the same as what you got from thermalization of this pure state, and also roughly the same as what you would get from the maximally mixed state of the system. Okay, and this is not really enough to establish that it really looks thermal. I'm only showing you the entropy is similar. You can make a more detailed study, but I'm going to not do that here in view of time. And to really convince yourself, you want to scale the system size up a little bit and see larger sizes and do some finite size scaling. So just to show you an example of what happens when you don't have chaos, let me consider another model where now I make the nearest neighbor coupling the dominant one, so I turn off all other couplings. So this L naught is equal to 1 now. And I make the random field very, very large. So this describes a phase of matter which is called a many-body localized phase. It's a phase that we believe is not chaotic. It doesn't thermalize. It doesn't have information spreading, or at least much more slow information spreading. And so what will the statistics of the level spacings look like in this case? Anybody have a guess? Maybe someone knows. No one has a guess? It's like a Poisson. There it is. You know, there's substantial finite size effect here, so, you know, this shouldn't necessarily convince you to, you know, make $1 million bet on this fact. But there it is. It's substantially different from the random matrix ensemble and looks much more like Poisson. And why is that? Why do you get random matrix versus Poisson in these different cases? Well, the intuition in the chaotic system is that you have many closely spaced levels. And now imagine I change the Hamiltonian a little bit. So there'll be some matrix elements between these different energy levels. But because the matrix elements are, you know, of some finite size and level spacing is so small, if you think in perturbation theory terms, the perturbation is really dramatic, right? Because you're adding a small perturbation. You're adding, you know, changing the energy, the coupling by 0.01, but the level spacing is really tiny. So it's a really large perturbation. Everything gets completely scrambled around. And so you might sort of think that you get something kind of random looking. If you're sort of following the dynamics of these energy levels, they're kind of interacting all the time, bouncing off of each other as a function of parameters, so it kind of looks like a chaotic dynamics. But for this many-by-localized state, the physics is that energy levels with nearly the same energy have very, very small overlap, very small matrix element with local operators. And so now the matrix elements are smaller than the splittings in some typical sense, and you actually don't get effective level repulsion. And that's why it looks Poisson-like. In many-by-localized.
In principle, you can just cut out the similar state which has similar localization pattern. Then you get random matrix again, right?
Sorry, which state?
For example, in many-body localized system, you can imagine Hilbert space is split to various localized
Yes.
configurations. And you can, you know, for example, air can be localized around the Earth or.
Yeah.
And if you just cut out Earth, it's just chaotic.
Yeah. I mean really many-body localized state.
Yeah, so if you restrict Hilbert space to local, you know, specific localized configuration, then I would think you again get random matrix. And I always wonder if there is any essential difference. Also appears because the spectrum around the Earth and the spectrum around the Mars are just independent, right? Then of course we get Poisson.
Oh, you mean the I'm not sure I understand. The localizing some degrees of freedom in some region of space, like via some potential, is not the same as like a many-by-localized state, right?
It's more complicated.
It's more complicated.
But essentially in terms of Hilbert space, probably you can have similar.
I'm not. Okay, I'm.
I'm tonight, so I never.
I'm not sure I fully understand your question. So maybe let's talk more about it after. Okay, now in this case, what do you think the entropies look like for these different energy eigenstates? Anybody have a guess? No guesses? Will they look thermal? Will they look not thermal? Not thermal. Hey, somebody's brave. That's pretty not thermal. So now this is the entropy as a function of energy again. But remember, the previous curve is like this rainbow here. Now actually you find, even at the middle of the spectrum, you find entropies of all different sizes, right? And so there's a strong sense in which this is not thermalizing because even states with roughly the same average energy have all kinds of different entropies.
In some of the lectures, some people like oppose chaos to glassy behavior. Glassy behavior will be something dislocalized.
Yeah, I mean, I think classically with some just fixed random media, you don't have localization. You'll just have diffusion. And so you'll still have a notion of thermalization in that case. This many-by-localization is really some kind of quantum interference effect, which I think is not really present classically. Although, you know, we should be a little careful. There's a notion of classical glass and getting stuck in configurations. So
But the distribution in values would be something like Poisson or something.
I'm not sure, actually, in general. I'm not comfortable making a general statement about that. Just to show you this local versus non-local, let's look at the non-local model. This is the same thing we showed before, where you had some notion, looked like it was scrambling. Here's the same spectrum. And again, you see it looks GOE-like instead of Poissonian. Okay, so this kind of is some small evidence that local versus non-local does not matter with respect to this late-time random matrix structure. Now, if I turn off this field, something dramatic happens. It starts to look more Poisson-like. And this Hamiltonian without the field is sort of, it's a cousin of spin glass Hamiltonians, where you essentially have many degenerate, nearly degenerate states. And this is sort of like the random Heisenberg model, which is believed to be a spin glass. And so this may be a manifestation of that glassy physics there. So this is to say you can get all kinds of different behaviors in these models by tweaking the parameters. And if you make them generic, you'll often see either one of this GOE or Poisson or some other random matrix. But even in finite size, you can see, the spectrum can be messy and doesn't look clear like any of them. So it's not always clear what's going on. Okay, let me talk now about the spectral form factor real quick. So here's the definition. Again, I average the time evolution operator. I take this trace over the thermal state, and here I'll just set beta equal to 0, so I'll look at infinite temperature, like we've been doing. And here's the form factor, and here is the connected part of it. And so I'm going to do it again for this model. This is, again, why I introduced this disorder. It's a convenient tool to average over different realizations of this form factor and smooth out the fluctuations. And so I'll just show you that spectral form factor for this model with this small disorder. So here's what it looks like. This is the long-range model. I mean, the power law model. There are 11 sites. You can make it bigger. This is just, if you run it on your laptop, it will run in 5 minutes. So it's nice. 200 samples, so 200 realizations of disorder. I do that averaging. Then I take the log and I plot it here. Okay, so what you see is it starts out, this is the log, so it starts out close to 1, or identically at 1. It very, very rapidly drops down. Then it rises again with some power law. Since this is a log plot, a straight line is a power law. And then it sort of plateaus out. In the SYK study that appeared recently, this was called the dip, then the ramp, and the plateau. And the ramp and the plateau are, well, so let's say the ramp especially is a feature of the two-level correlations in a random matrix. Random matrix theory will predict that you get a power law here with power law, with the power equal to 1. And if you analyze this data a little more carefully, you can indeed see that you get an exponent close to 1 in that case. So this is sort of showing you that the two-body correlations of the energy levels in this state are like those of random matrix. And again, you can do this for the non-local spin model, you can do it for SYK, and it all looks fairly similar. The early time part is more variable, but the late time ramp and plateau seems to be a relatively universal feature of chaotic systems. And so in some sense, this linear growth is one answer to the question of what's happening in intermediate times between scrambling and the exponential time at which things sort of saturate out here. Is that you're sort of probing more and more finely the energy level spacing, and that's reflected here in the growth of this spectral form factor. We also think, based on ideas from ADS-CFT and elsewhere, that this kind of late time region is associated with the growth of complexity of the state. And so one conjecture you might want to make is that this linear growth is somehow related to the growth of complexity. That's a very tempting conjecture to make. Now, by itself, this is not a true conjecture because in a very nice paper by Jordan Kotler, who's here, and Benny Yoshida and others, they showed that if you really did the same thing for a random Hermitian matrix, that you would see still the ramp and plateau, But they were able, via a counting argument, to show that the complexity grows quadratically with time, which is not what you want for holographic. So just the ramp and plateau by itself will not tell you that you have linearly growing complexity. But maybe if you also add the physics of locality, you might imagine you can prove a theorem that says if you have local Hamiltonian and if this thing grows linearly with time in this form, then the complexity is also growing. Yeah, that's probably some insanely hard thing to prove. Maybe it's independent of the axioms of mathematics. I don't know. But that's kind of what we sort of think is true. That's a reasonable conjecture based on our current state of knowledge. Okay? Questions about this stuff? Yeah?
So you were saying that non-local and local Hamiltonians generally produce the same sort of late time chaos, but you think now this might differentiate this ramp and slope, or am I not following correctly?
No, so yeah, sorry. What I should say is that local versus non-local, but still few body, we believe those all have a linear growth of complexity with time. Now that can be distinguished from this random Hermitian matrix case, like really many-body random Hermitian matrix, in which case the interactions are very non-few body. They're many-body interactions. That is, every component of the Hamiltonian matrix is non-zero, but the typical size of it is exponentially small. And that is what they could show by this counting argument, on average, has complexity that grows quadratically with time. So you would need to add the physics of few bodiness. Yeah, you see, I said locality, didn't I? I'm getting tricked with this quantum information. It's always very tricky. You would need to add the physics of few bodiness, but not necessarily geometric locality, plus this random matrix, perhaps, to see something like linear complexity growth. That would be one hypothesis that I would put forward. Others have put forward similar hypotheses, and you could try to validate that in some situation. Other questions?
Is the idea that black holes may not exhibit locality in their interior at high energies, but still just few body interactions?
Yes, that's right. So yeah, to give a concrete example of this, if you imagine a gauge theory, a large N non-abelian gauge theory, then think about a lattice model of that. On every site, there are many colors, and the color interaction is non-local. Every color can talk to every other color. But there's still also a notion of spatial locality between the sites. So there's two kinds of things happening in that model. There's non-local dynamics on the site and local dynamics between sites. And you can see the same thing in ADS-CFT. The scrambling will go from this kind of log n behavior to a linear and separation behavior when you go beyond sort of the ADS radius. So yeah, we believe that there's these different kinds of phenomena in the black hole happening. Okay? So let's talk about experiments in the last little bit. As I said, to do these experiments, you usually need a time machine. Here's a time machine. And unfortunately, this time machine is hard to find. However, it turns out that they're actually making more of them, I discovered. So maybe we have a chance. So what kind of platforms can we consider? So I already talked to some extent about the NMR platform. This is sort of one of the first places where this echo kind of physics was observed. Still a very valuable platform. But in modern experimental physics, there are lots of other possibilities where we have also the possibility of having a very high degree of quantum control isolation that we could achieve. But one of these is a trapped ion. So this is where you take ions and trap them in some kind of oscillating electromagnetic field. You have optical lattices of neutral atoms. So you can make standing waves of laser beams. And because of the polarizability of these atoms, they prefer to sit preferentially at certain points of the intensity. And you can trap them in some effective lattice. People have considered Rydberg atoms. So this is like atoms where you highly excite either virtually or physically between some low-lying level and some very high level. And the reason why this is interesting is because if you recall from your first quantum mechanics class, these Rydberg levels, these very high levels in hydrogen, have very big wave functions. So you could engineer interesting kinds of interactions where you can vary the strength of the interaction in an interesting and controlled way. Now you also have what are called cavity quantum electrodynamics platforms. This is where you can trap bunch of atoms or some other kind of system inside an optical cavity in which light can resonate, and you can couple the atoms strongly to the light and use that light to mediate a kind of non-local interaction between the different degrees of freedom. And there are others. I won't really go through these things in detail. And in various of these platforms, it's possible to do various things you need to do to implement these kind of echo or out-of-time order correlation experiments. So the key aspects, for my purposes, are essentially the system size, the complexity, and the time scale. So you see it, and if an experiment can do if experimentalists can do an experiment with 5 particles, that may be very nice. It may be a nice stepping stone to understand how to do bigger experiments. It may involve some very clever experimental trick. It may be an important development. But nevertheless, from the point of view of the physics, I can simulate everything on my computer in 1 minute. And so I'm not learning anything about the physics of 5 qubits that I couldn't learn by using my device right here. So one thing we would like, ultimately, this is a desiderata, not necessarily the only desiderata, but one is to have sizes that are large enough that it's not easy to just exactly simulate what happens on your computer. The second thing we need is, even if the size is large, the complexity can be low. So for example, if it's a bunch of decoupled spins, I don't care how many of them you have. You can have 1 million of them. I can still simulate the physics on my computer very easily. So we also want the system to be of sufficient complexity that something interesting happens and we're really probing the many-body physics. That's another desiderata. And the third thing we need is that the time scale is sufficiently long, because even in a big system, even in a complex system, if times are short, I can still simulate. So I want to emphasize again, I'm sort of speaking in terms of classical simulation. I'm trying to take this kind of sort of information theoretic simulation point of view, where the criterion is I want to probe physics I can't probe by just programming MATLAB on my computer. There are lots of other reasons why you might want to study these kinds of systems in which there are different goals and different desires. Okay, this is the desire if you want to discover qualitatively new phenomena of quantum many-body physics. If you want to probe scrambling or chaos in systems of 1,000 spins, this is what you need to have. There are already lots of experiments which can probe these kind of long times, relatively speaking. Times of order 10 or 100 inverse J, where J is some sort of characteristic energy scale in the Hamiltonian. And so that would be enough time to, say, observe this early time decay here, perhaps. But not enough time to really see much beyond that. And certainly not enough time to see anything exponentially long in system size. Okay. And so I think a natural next step, if you sort of grant that experiments have now reached sufficient size, complexity, and isolation, that they can reach this kind of time scale, then we can say we've sort of seen this physics. I mean, there's still more to do here, but we've sort of seen that early time physics. The next natural step is to try to look for scrambling. So that's what I'll talk about in the remainder. And so how could you actually measure these things? Well, this is a version of that sort of echo-like experiment that I talked about before, where we want to measure now, let's say, an out-of-time order correlator. We've already been able to measure 1-point functions. We've seen them decay. What about, and we can see 2-point functions decay as well. What about 4-point functions? And to do this kind of measurement, there are various tricks, but one trick is, again, to introduce this idea of some ancilla, some probe, some control. So I want to think of the out-of-time order correlator as an overlap of 2 different states. One state here where I apply a perturbation, then I go forward in time, apply W, and then go backwards in time. That's this. So I apply perturbation, go forward, apply W, go backwards. And then another state here, where I first go forward in time, apply W, then go backwards and apply V. Right? And that obviously measures the degree to which V and W fail to commute. Because if they commute, then these are the same state, and the overlap is 1. So we'd like to find a way to essentially make an interferometer where on the 2 arms of the interferometer you have this state and this state, and then you can measure the interference and get the overlap. And a way to do that is to put a little extra degree of freedom here, 1 qubit, such that the state of this qubit controls whether you apply V before or after the application of W. That's one simple way to do this. And so this led to a proposal by myself and my colleagues at Stanford at the time. Well, I was at Stanford at the time. Of a precise sort of quantum circuit picture of how to make this measurement, and then also an associated set of physical systems where we thought this was a possible thing to do. Okay, and so there's some precise procedure. I won't go into the details of it. You can read in the paper. There are lots of other ideas for how to do this kind of OTOC measurement. And I emphasize that this is on top of the already existing measurement schemes for various kinds of Low-Schmidt echoes and the existing literature in NMR and other communities. Here we're sort of focusing really on this sort of local physics, on local control, which is something you don't necessarily have in general without some of these more sophisticated techniques. So like the ability to address a single atom is something that's relatively new and actually still being developed. But that's the kind of thing you might need if you want to probe, say, the growth of chaos from one point to another point. You need local addressability. So here's one sort of simple model where these things can be engineered. This is a model that has a rich literature, which you can read about in the lecture notes. The key point of this model is it's one of these cavity QED models. And the setup is basically you have some mirrors here. And these mirrors confine some light field, strongly confine it. And the light field has some kind of beam shape here. And if the beam is tightly focused, then the light is very intense at this point, and you can get a strong atom-light interaction. Right? So then if I place an ensemble of atoms here, the atoms can interact strongly with the light field. The light field's bouncing many, many times, and so I can generate an effective, strong, non-local interaction between different spins. So this is an example where, although nature typically gives us local interaction, we can, by engineering the system appropriately, generate non-local interaction. And the kind of interaction you can generate depends on the parameters of the setup here. I won't go into all the details. There's various laser fields and detunings, these deltas, little delta. At the end of the day, when you do this kind of perturbation theory process, you find that you get a Hamiltonian which contains all these various parameters, the laser strengths, the detunings, the shape of the light field, and this two-photon detuning, and some kind of spin-spin interaction. And so you can generically engineer states that, Hamiltonians that look a lot like what I was showing you before, where I either have some kind of, local interaction or some very non-local interaction, depending on how you shape these fields. And some crucial things is that I can actually change the sign of this Hamiltonian by changing the detuning little delta. And various other kinds of control operations are possible. So this is one setting where you could actually do these sorts of measurements. Okay, you can benchmark this. This is a little boring, so I'm going to skip it. You can make a sort of simple chaotic model that you can try to study in this setup, something experimentalists have already tried to do before. And you can try to see, say, the physics of classical chaos, the classical Lyapunov exponent, in some kind of many-body experiment. And so you could try to measure, say, these time-ordered correlators at a time-ordered correlator. And what you might want to see experimentally is that the time-ordered correlator decays on a time scale which is roughly independent of the system size. The different curves here, different colors, are different system sizes. So the time scale for the decay of the two-point function is independent of system size. That's what we said before. It's an order 1 time. But the time scale for the decay of the other time-ordered correlator depends on system size. So as I make the system size bigger, the correlator gets larger, the decay takes longer. And here, this is sort of like a large spin, a large collective spin. So it's like a semi-classical system. And so it's like the dynamics, the chaotic dynamics of a semi-classical particle on the surface of a sphere. And so you can try to estimate that the time scale here for this out-of-time correlator to decay should be roughly like the log of the system size, the log of n, and you can try to observe that, or some signature of that. Okay, so there have actually, since this proposal, been already 4 experiments that have been performed. One of them was an experiment using trapped ions. One of them was an experiment in a small NMR setup. In both of these cases, so here, the experiment involved more than 100 trapped ions, so two-level systems, which is great as far as system size is concerned. However, the Hamiltonian they implemented was just this total Sx squared Hamiltonian, which is not chaotic. So the complexity is not there yet. The dynamics is easy to describe on my computer, so it doesn't meet my bill, my list of desiderata. Now here, they actually have a Hamiltonian which is chaotic, we think. It's like this model I showed you, but there's only 4 spins. So again, you know, it may be a stepping stone to something bigger, but at the present time, I'm not learning anything about many-body chaos from this model. There was also another experiment a little bit later with some NMR technology in molecules with chain-like structure, in which they studied the physics of localization. This was actually a sort of interesting experiment. And then there was another experiment, I'll comment on it more in a second. There was another experiment where they tried to do, again, this kicked top model with some BECs, where actually different momentum states of the BEC were mapped as spin states. So they had a very interesting setup there, but the system sizes were still small enough that one could simulate the physics exactly. However, one thing you can say about these experiments is that they're giving us valuable insight about the kinds of effects of experimental imperfections and other degrees of freedom that we need to control in order to ultimately see the physics of chaos and scrambling at larger sizes where we want to explore new physics. So I'll just show you one plot from this from this paper, which is a plot of what they call the correlation length as a function of time, here in milliseconds. This correlation length is roughly the average weight that I defined yesterday. So it's the average number of non-zero Pauli operators. Because this is an NMR experiment, so they don't have any local control. They can't image single sites. They just sort of see globally how the state is evolving. And so this is roughly speaking the average weight. And so what you see as a function of time is that this weight grows. And if they turn off the interaction so that the particles, so that the spins are equivalent to free particles, so there's no complexity at all, then the operator weight growth saturates and becomes essentially constant. This is saying if you have a single field operator or a single fermion operator and you time evolve it, it just turns into other fermion operators. It never becomes a 2 fermion or 3 fermion operator. So the number of fermion operators present is maxed. However, when you turn on interaction, you can get a localized state, a many-body localized state. And in that state, we believe that things grow logarithmically with time. And okay, they have 1 decade, which they plot on a log scale here, and it looks somewhat consistent with a straight line on that log linear plot. So I'd say this data is consistent with a logarithmic growth of operators in a many-body localized state, but they don't have a lot of dynamic range, and it's still a small system, but we're starting to begin to see some of the physics of operator growth in at least a non-chaotic but relatively large system. Now I'll draw your attention to 2 other experiments which just appeared late last year. In which they've studied even larger systems now with Rydberg atoms and trapped ions of 50 qubits. And so they have a sort of large size, but they also have sufficient complexity that things can get interesting. So actually in both these cases, the Hamiltonian is in this roughly the same universality class as the non-local spin, the power law Ising model I showed you. So in both cases, they have Ising interactions where they can control the range of these interactions, and they can add various kinds of fields, longitudinal fields and transverse field. So I'm not claiming the physics that you see in these things is chaotic. They're actually interested in some benchmarking, which is a sort of a different type. But the Hamiltonians are of a class that could show the kind of chaos we've been studying here. But they haven't measured out of time order correlators yet, and it's challenging. The other thing I'll mention is that you have to take very seriously the effects of dissipation, of noise and imperfection in the system to see to what extent this kind of measurement is actually possible. And so you can do an analysis of typical kinds of loss or decoherence in your system, for example, in this kicked top cavity QED. I just want to flash this. I'm not going to explain all the physics here, but just to flash, to tell you that this is the kind of thing you can worry about and you should worry about, and it's an interesting way to spend your time as a theorist, maybe not all your time, but some of your time thinking about what actually happens in an experiment. I know that's a pretty novel concept for this group, but it can be quite fun and very interesting, and sometimes you discover something interesting. Like here. Suppose, for example, one imperfection is you're trying to do your experiment, you have your grad student, and you tell the grad student, okay, at every hour, turn the knob to +1, that's forward, and then every other hour, turn the knob to -1, that's backwards. But the grad student has been doing this for a long time, so they're kind of tired. And their hand gets kind of shaky, and they turn it to +0.9 instead of +1. Or they accidentally bump another knob and change the Hamiltonian a little bit. So what if the forward evolution is not the same as the backwards evolution? Does that completely destroy the physics of out-of-time order correlators, or can you still observe what you want to observe? And it turns out, this is again actually something that people in NMR do, which is sort of normalizing by some kind of echo physics. But what you can see here is that I show in blue the out-of-time order correlator, or the log of 1 minus it, so the early time growth, for a case where I have my power law Ising model, and I go forward with Hamiltonian and backwards with the same Hamiltonian. So it's a perfect reversal. And then I do the same thing where I take that Hamiltonian and I add to it completely random fields in the z direction and completely random z interactions of size roughly 20%. So this is a substantial modification of the Hamiltonian. This is like changing all the couplings by 10% between forward and backwards. Nevertheless, if I take this ratio of two different experimentally measurable quantities, which is the imperfect out-of-time order correlator with both operators present and the imperfect out-of-time order correlator with only one operator present, I take the ratio of those two quantities, I get this yellow curve, which actually adheres incredibly closely, even on this log scale, to the desired result. Okay. So it seems like there is a way to actually normalize out the imperfections associated with going backwards and forwards. And the red shows what you would get if you didn't normalize that out. You see the slope is totally different. In fact, the whole behavior looks different. And so this may be one part of a very important, of many different experimental tools we need to ultimately observe this physics in some sufficiently large system. But I think also the reasons why this works are also somewhat obscure. So I think this is a theoretical problem as well to understand why this subtraction, or this ratio, works so well. And it seems to work well up until the scrambling time. And so roughly our picture is that somehow before the scrambling time, there's two different physical processes happening. There's the decay of the overlap, which is like the echo, and there's the growth of operators, which is like scrambling. And these two processes are kind of independent from each other. And then after the scrambling time, they get mixed up. But before the scrambling time, you can kind of normalize one away. But that's just a sort of conjecture. In fact, it can work even if you have errors from shot to shot. So suppose your grad student is flipping the knob differently every single time. You can still do the normalization, which is really remarkable. Okay, now I'm basically out of time, so let me just show you some pictures and talk about what all of you can do with your time if you want to study quantum chaos. Okay, first question is, are there different universality classes of quantum chaos? Is there just one kind of quantum chaos? Are there many kinds of quantum chaos? And related to this, can we relate early time properties of quantum chaos to late time properties? Do Lyapunov exponents, do growth of out-of-time order correlators imply random matrix theory and vice versa? What assumptions do we need to make for that to be true? And related to that question, are there different kinds of chaos? Is there just localization? Is there just integrability in chaos? Or is there chaos 1, chaos 2, chaos 3? What's the sort of zoology here? And, you have to be careful because even people at NASA can get confused about whether liquid and gas are two different phases of matter. They're actually the same phase because they can be connected without a phase transition. So although they have seemingly very different properties, you should be careful about declaring two things that seem different to be truly different because sometimes there's a clever way of connecting them. Another thing that I like to think about is emergent speed limits. So this person is experiencing an emergent speed limit due to a strongly interacting gas of sheep. And so this kind of physics can happen also in quantum systems. And out of time order correlators, the growth of chaos can diagnose speed limits. It can tell you how things expand in space and time. And so if those correlators are small, then it may be that information is spreading slowly or not at all. Understanding those kind of speed limits can be very interesting for a variety of purposes. For example, this is related to the way that causality in the bulk emerges from causality on the boundary in ADS-CFT. There are also questions about how, I'm not sure what this box is. There are also questions about how scrambling manifests itself in more ordinary observables that we care about in strongly interacting many-body quantum systems. So for example, here I show measurements of longitudinal resistance in quantum Hall systems. These are the kind of systems that display anyons, topological physics that Frank was talking about. There are also high-temperature superconductors where there are various mysterious transport phenomena. Does chaos have anything to do with quantum transport? Can we use it to provide bounds on transport? Are there any relationships? This is another very hot topic. We know that black holes have a lot to do with chaos, classically already. I mean, the environment near a black hole is usually a very dangerous and crazy place. But we also, of course, know in recent years that quantum dynamics of black holes also closely related to quantum chaos. So I think there's still a lot to understand about what the significance of maximal chaos is for quantum systems, what it implies about the existence of gravity or not. That's another very interesting direction. This is a volume of Landau-Lifshitz from the future. It has yet to be written. It's also edible. It's a cake. And so, you know, one of the questions we saw was there was a growth of entanglement as a part of the process of thermalization. And I mentioned this Kolmogorov-Sinai entropy, which is related to the growth of chaos in classical systems. So is there a connection between the growth of entropy, the growth of entanglement, and the growth of chaos? There should be some relation, but we think we still in the early days of understanding that relation. So one of the chapters in this book will presumably be about the relationship between entanglement and chaos, and that chapter is still largely unwritten. Other questions include how to simulate this physics using large-scale numerics. So I showed you one example using tensor networks where we could actually capture the dynamics of operators for very large chains, much larger than you could do using, you know, your sort of exact diagonalization procedure. So are there other ways of understanding how chaos manifests? And can we use chaos to help us do simulations of interesting systems? For example, black holes thermalize. Can we somehow use that thermalization as a tool to go to longer times than we could otherwise? Because black holes sort of look effectively thermal. So can we find out how to make things sort of look thermal to reduce the entanglement in some way? You know, there's excitement coming from the quantum simulation community. So this is like the quantum simulator experiments I showed you before, where we're able to construct larger and larger and more elaborate many-body models. Here, it's actually a Hubbard model of fermions with spin, and you can actually observe antiferromagnetism, so the anti-alignment of spins for the first time. Here, the challenge was cooling the system down to low enough temperature to see this physics. And so there are lots of interesting questions of an experimental nature about how to actually realize chaos, quantum chaos, in these sorts of many-body quantum systems. What observables should you look at? How should you probe the physics? And finally, of course, there's lots of connections to quantum computing. We already had the conjecture that black holes are the fastest computers in nature, whatever that means. That seems to not be quite true, or at least we're not sure how true it is. But there are lots of other interesting tasks in quantum information science you might want to think about. For example, one interesting task is sampling from a distribution. So maybe if a system scrambles rapidly, it sort of moves over the space of possibilities very quickly, and it's useful for sampling things in a very random way. Maybe scrambling can be used to produce random numbers in a very fast way. Maybe scrambling can be used to explore the space of possibilities for search in a rapid way. So I think there are lots of connections here between, lots of potential connections between the growth of complexity, quantum chaos, and information theoretic tasks you might want to achieve that, you know, are sort of, there's lots of possibilities and not a lot known. So it's a great place to work. Okay, so thanks.